Honey.
Hi, Victoria.
Hello. We meet again on the stage.
Yes. It's a nice
Oh my
day.
gosh.
How was your day so far?
Yeah, it's beautiful. Hopefully my reception is better this time. Hello, Jamie.
Hi, Victoria. How are you?
Good, thank you. How's your day?
It's been going well, thank you. Oh, hi, Katerina. So this looks like an interesting talk today. I'm looking forward to it.
Very.
It's one of these topics that you would think I would know more about, but I don't. Like the current thing in the Atlantic Ocean. I don't know anything about that. I mean, I just always thought, yeah, it's got current, and I've kind of left it at that.
Well, life's like that, you know? When something comes up, when you realize where the gaps are, what you want to know, and you do a Google, and then you learn.
Yeah. How did we even survive with a database of the size of Google?
Probably
How did
would go to
how
the
did
library a little bit more.
That's true. That's true. Side note, it's a shame that I'm seeing over where I am, libraries being, physical libraries to go in and see books and things to be, they're being prioritized less and less because of the sheer um movement of everything being a keystroke away online.
Well,
And it's
I don't think it's that. I think it's because, I mean, where I live, it's funding. It was libraries were having a really hard time because there was funding that was paying the library workers, and then that was cut, so they had to close libraries down on weekends, starting with one weekend day. And I know a lot of times, people that would be the outing. I know many families that would go to the library for something that they're doing on a Sunday, and then everybody comes home with a lot of books and hangs out and has fun. So it was really a funding problem.
really, oh man, maybe I'm not understanding all the angles, but that's really sad that like how funding's being cut for something so important.
It
It's a
is. It
shame.
is. It's sad choice for funding priorities. They shouldn't for public services like that shouldn't have to be juggling, between firefighters and libraries and water utilities and um, yeah. But that's a talk about the benefits of
Uh,
socialism, which we're not doing that here today.
yeah, no,
Some
I
other
did.
time. Sister Rahim,
That's totally
hi.
right. Hi, Sister Ian.
Hi, everyone.
Have you been, Sister Ian?
Very busy, but hanging in there.
Hi, everyone. We'll start in around 5 minutes. Thank you for coming. Oh, I wanted to also tell everyone we really only have 16 minutes. We have a hard stop because our guest speaker has another appointment after this, so or we have to moderate accordingly. So for now, I guess later it will be probably a room where people want to ask a lot of questions and comment, but let's keep it at one question comment per person, and then we'll see how it goes from there. Thank you.
Thank you for the heads up.
Thank you, Katerina. No problem. The difficulty will be thinking, which one question can I ask? So many! But I could see this having a bigger discussion, like in a roundtable thing later on. Even just looking at the title of this particular talk, I'm actually really curious. I know you'll probably be touching on what this will do to the ecosystem, because I bet you so many different creatures probably like live and thrive around the current in some way, I bet you.
Well, one thing is that currents bring food.
Mm,
So if you're
mm.
thinking, even currents bring food even in the form of chemical food. So, oh, here we go. Here we have somebody we want to welcome. Welcome, Matthew.
Hi, Matt. Thank you for coming. The unmute button is all the way on the bottom right hand. There should be a little.
Yes, I got it. Thank you so much.
How are you today? Thank you for taking.
Well,
I'm great.
welcome, Doctor.
Thank you.
Welcome.
Thanks, everyone.
Okay. We'll start in 1 minute, everyone. So, yeah, thank you so much for coming. Okay, I think we can just start by introducing you, and then we'll go from there. So welcome everyone to the Science Society. I'm really honored to introduce you to Dr. Matthew England today, who is presenting his really important work today here, and sharing and answering questions. So thank you so much, Matt, for coming. And let me give the audience a little bit of information. So Dr. Matthew England, he's at the UW Climate Change Research and Center for Excellence in Antarctic Science. And he did his bachelor in science with honors at the University of Sydney, Australia, and his PhD also at the University of Sydney. And he he received many awards, many, and published a lot of work, and his research explores the large-scale ocean circulation and its influence on regional and global climate. And he has a particular focus on the southern hemisphere, including the Antarctic climate processes. And he uses ocean and coupled climate models in combination with observations and theoretical approaches. And he studies what controls ocean currents and how these currents affect climate and climate variability, the timescales of seasons to millennia. And his works applications are very broad, and it's we are really honored to have you here. And if it's okay with you, before we go into your research, Victoria asks usually our guests a couple of questions. And yeah, and then the stage is yours to give maybe a short or an introduction of your work, and then go into the Q&A. Thank you so much.
Thanks, Katarina. That sounds great.
All right, then let's have at it. So, welcome, Dr. England. Science Society is so happy to have you here and hear more about your research into ocean currents. And we'd like to hear a little bit about you to carry us into the body of your research. And to do that, my question is, can you think back to a time in your life that you noticed that you felt a particular affinity towards science, and it doesn't need to be, an ocean-related affinity, just any time that you felt that science was something that you really connected with.
Yeah, it's a great place to start. I think my interest got sparked. Actually, it was the same time as I got interested in the oceans. I became interested in science. I actually lucky enough to grow up in Sydney, Australia, where we have beaches and some amazing marine life and rock pools. You can go down to the tidal zone at many of the beaches around on low tide. You've got beautiful rock pools, and you can fish and algae and tiny fish swimming around. And as a sort of 3 or 4 year old, when my parents took me to the beach, I used to sometimes terrify them by leaving our little spot on the sand there myself off to the rock, stare at them for hours. And I mean, it was back in the day when kids would just wander off and do their own thing a bit more than today, maybe, but they'd eventually find me and know where to look for me. And I think I always dreamed of being a marine biologist from that early age. But in the end, my own work at school, I somehow got really into maths and physics, and yeah, that led me into oceanography eventually, which is actually more a study of the dynamics of the ocean, so how they move and why they move, and when they move, what do they do? Do they move heat somewhere, or do they melt ice, or do they change the atmosphere in some way? And so it was a long journey, but it started in those rock pools off Sydney, I think, where I got to look at the natural world. And I think a lot of students who get into science probably start with something like that, whether it's gazing up at stars in the night sky, or trying to understand why a mountain might be where it is, or you know basic biology or chemistry or physics or earth sciences often draws young students in. And that's a great thing, because we do need more scientists in the world, and I think they generally contribute back to society with this understanding of our natural world and of medicine and all these sorts of disciplines.
Thank you. Thank you. That's so interesting to hear that. And we do hear often people talking about something from their childhood and the discoveries that people made during play, and then what the people were wondering. Exactly that somebody wondered about the night sky, exactly as you've said. And because it it just shows how important it is to have unconstricted playtime, unconstricted time in the natural world.
Yeah, for sure.
And yeah, that's why we're here with Science Society, right? To share that love and feed that interest and inform people. So we really appreciate that you're here. And if you can then take us along your path, just maybe with some brief stops to how you arrived at the point you are today in your research.
There's also a bit of a storyline to that too. I mean, I gave away a little bit of it. I ended up in school somehow picking up on. I loved maths. I loved the way you could, start a problem and prove the solution at the end. I loved the somehow the preciseness and exactness of it, and also the puzzle solving nature of it. So somehow was drawn to that, and I always loved English and history as well. But I just I somehow didn't find them as easy to do, or and writing. So it's funny. I'm sure that they were such useful subjects to take on. I guess a lot of people might do this. My first few years at university, I was more just enjoying being a university student, really, and connecting with other people my own age, and I got really into surfing. So board riding was a big thing that became part of my life in my late teens, early 20s. Every university holiday, I'd venture with friends to the nearest surf break, and sometimes spend 6 hours a day just surfing waves. And I got so into being in the ocean, both as a swimmer and a surfer and body surfer, and I was really floundering in this university degree where I just was doing maths and physics, and I didn't know where it was going to take me from a career perspective. And it was a total accident. One day I was looking at what subject to take next, and fortunately the fellow Matt Tomczak, like a big phone directory, like it's just plain text, there's no photos at all in this whole photograph of a wave. And I was like, what is a wave and a surfer doing in a handbook on university subjects? And that's why I discovered this field of physical oceanography, which is the study of the physics of the oceans, how they move, the waves, the turbulence, the mixing, the heat transfer properties, how it interacts with the climate system, tides, all these things that have been studied for, in some cases, tides dates right back to Aristotle. Other aspects of oceanography are only 50 to 100 years old. So this was it kind of saved my university degree and got me into this career kind of by accident, but it really harks back to the rock pool story I told you at the start on the beach of Sydney. So I got to do marine research in the end, but via this pathway that took me away from biology and into the physics. But it was a wonderful field to discover because it was all about ocean exploration, and I got to go on as a in my 20s, across from Africa to South America on one trip, from Australia down to Antarctica on another trip, and then from Hawaii to Tahiti, then right across we basically trekked across the equator. We stuck to the equator right across the Pacific from east to west, which relates to some of the science that we're going to talk about in a sec. But that sort of ocean voyage work really drew me into this field of global scale physical oceanography, and that's all about the global scale circulation. So the movement of water from the tropics to high latitudes, the regulation of Earth's atmosphere, the melting of the ice caps under climate change. All of these topics are in this branch of oceanography, which is not so much concerned with a small coastal current or a flow within a bay or a harbor. It's really about the open ocean circulation. I sometimes say to people who want to understand what I do is that if I'm on a boat and I can see land, I'm probably not somewhere where I'm interested in the ocean circulation. It's all of the oceans that's basically remote from land, except probably around Antarctica, because we really want to understand the ocean flow right up against the Antarctic margin.
It sounds though like that you're viewing the ocean holistically and not, as you're saying, as a particular current in any one place.
Yeah, that's
This
a really
is
good way to put it. Yeah, no, it's a really good way to put it, Katerina. Sorry to cut in. I just to sort of say it's a holistic approach, because not only do we look at the circulation on these global scales from tropics to the poles, from the Indian to the Atlantic to the Pacific Ocean, but we also then it's also holistic in the sense that we really need to understand the atmosphere as well, because sometimes these messages or these teleconnections from one basin to another, they may occur via the ocean, but sometimes they take a shortcut, and it's the atmosphere that transports this information from one basin to another. And that's part of the topic of the paper that we'll discuss. Or it might be sea ice or the ice margin in Antarctica. And so we actually have to not just think about the oceans, but also all of the atmosphere from pole to pole, and also all of the ice system. So if I was to summarize what I work on these days, it's really the global coupled ocean atmosphere ice system.
right. That's a beautiful phrase, and the dynamism there within. So I don't want to get in the way of your delivering your talk anymore. And I thank you so much for those answers. And at this point, you may begin your talk. And if you'd like to have a Q&A at the end, then that's great. And if you'd prefer to have your discussion driven by a Q&A during, then just let us know. It's entirely up to you, and we are here to help moderate questions. And then we do have a hard stop at 1 hour, so everybody, when you do have questions, please limit them to one carefully chosen question. So thank you so much, Matthew. And we have your slides pinned at the top so people may follow along. And the mic is yours.
Yeah, look, thank you. And what I'll do, I think I'm happy to do, if that works for you. And Clubhouse is I gave a Clubhouse talk a couple of days ago, but this is my second one, so I know the system a little bit better than I did a few days ago, but still not too well. Katerina, if you're happy to, if there's a sort of discussion board where people can post questions, Katerina, I'd be delighted for you to interject sometimes and ask anything if things aren't clear. So I think me talking straight for 15, 20 minutes is probably not as good as people having the chance to chime in with a question, but it's probably best to manage with you moderating those, because if something comes up with a few questions, or anyway, rather than it just being open Q&A right through the talk, if you can moderate them, I'm definitely happy or others there who are running this talk, if you just chime in with a question, that's good for me.
Yes, always. It's never. You can relax and enjoy, and it's up to us, and we will definitely moderate carefully
Yeah,
and
perfect.
let you have
One
questions if you do.
really quick thing. It doesn't seem to be happening now, but while you were talking earlier, the audio was pausing. If that happens again, one thing you could do is change your audio to low quality.
Okay,
So
all right. That's in settings, is it? Well, let me
yeah,
know.
the upper right.
Well, it could also be if you're using your Wi-Fi. You could go off Wi-Fi. That's usually. I mean, I do that every time I'm in a room. It's a quick fix. Just go off
Okay,
Wi-Fi. Yeah, it
okay.
shouldn't. I
I'll
don't.
try that.
Yeah, you're probably not in music mode. So yeah, try going off your Wi-Fi, and that
What
should
I'll
work
do, I'll
great.
delete the Wi-Fi in case there are school holidays here and there are kids that are possibly, watching Netflix, or one of my daughters at university maybe streaming a lecture. So I'm just going to
Yeah, it's
kill
pretty
all.
typical
Let
on
me see. How's
Clubhouse.
that going? Yeah.
Sounds
Okay.
fabulous. Yeah, so we'll
Yeah.
let you know anything, and otherwise, just relax, enjoy,
Sure. Okay.
discuss, and
Yeah.
thank
So
you.
look. Yeah. Look. Thank you. And if everybody's got the paper there, I didn't put together slides because I thought better if you've got the paper. That's kind of the legacy of the work, to be able to look at that. And apologies. I know that all of the diagrams can be quite technical, but it won't take me too much time to talk through some of them. And so, yeah, look, the topic, just to start with, the topic of the study is on the Atlantic overturning circulation, and this is made famous by even a Hollywood blockbuster called The Day After Tomorrow, which was a movie about a scenario where the exact thing that we modeled played out. And in this sci-fi blockbuster, I think Dennis Quaid was in it, if I remember correctly, and others. Basically, the Atlantic overturning slows down, or actually collapses in a matter of days, and the whole world is plunged into a crazy climatic state. And whilst it was any good sci-fi takes a little bit of science and distorts it, and it becomes non-science in terms of fictitious things happening, it was still a really good film because it actually very accurately portrayed scientific debate. It portrayed climate scientists, a bit like this film Don't Look Up, but it wasn't comical. It was more like a sort of drama. But like the film Don't Look Up, it really portrayed the the plight of scientists calling out to the world the dangers of climate change. So I really would recommend watching it if you want to see a good cli-fi film, not quite sci-fi, it's cli-fi. Well, it's a genre of sci-fi that we call cli-fi these days. But anyway, on that very first figure 1A, you can see it's a cross section of the world's oceans, in the Atlantic at least, and it shows depth down the y-axis and then latitude in the x-axis, and you see a big red cell, and that corresponds to the sort of present day situation where we have a vigorous overturning of water in the Atlantic. So a lot of water moves northward in the upper ocean, and then it sinks around Greenland. That's why the cell sort of circulates around that red patch. And then the outflow of water then occurs if you look at the left-hand axis, from 2 to 3 kilometers depth. You sort of see this outflow of warm water that's brought to the high latitude and overturns. Now that circulation, it actually generates a huge amount of poleward heat transport, and that's what you can see in figure 1D. So the same figure, but down on the lower right, that black curve shows the present day, or at least in this model, and it basically matches up with the observations pretty well. It shows the present day overturning of heat in the Atlantic sector, and that's a petawatt of heat, which is a massive amount of energy going from the tropics to high latitudes. This moderates European climate. It keeps the European region so much warmer than it would be if the overturning wasn't present. And you just have to look at, say, a country like Portugal and the climate they have there, and then move across to Canada. And I think you hit parts of Newfoundland at the same latitude. And anybody who's been to both Portugal and Newfoundland, or even if you just look at weather maps, you'll know that there's a dramatically different climate at both places. One is at times freezing cold during winter, and the other is pretty mild year round, really mild during winter compared to the rest of inland Europe. And that's the oceans basically doing their thing of moderating our climate system. They're incredibly good at doing that because they can store heat, and they can transport heat thousands of kilometers, then release it to the atmosphere. And that's this overturning circulation's been probably the subject of, I would say, 1,000 papers. It's a very important part of our climate system. It's very important for European and North American nations because of the way it transports this heat. There's a lot of measurements that have gone on there, and so we know a lot about that circulation, and we know a lot about how it's affected our climate in the past, and we think we know how it's going to trend in the future, but there is uncertainty around that. It could do anything from collapse altogether. I think it could collapse altogether and into a sort of what we call an off state. And what I mean by that is it goes from these 20 units in that panel A there to more like 4 or 5 units of circulation. They're called Sverdrups after Hal Sverdrup. It's a technical unit, but it's basically millions of meters cubed of water overturning per second. So that 20 in panel A means 20 million cubic meters of water sinking every second, which is a lot. And so, look, we know a lot about this current. That we know that it's sort of switched off in the past during ice ages. We know that adding meltwater to Greenland, off Greenland, adding meltwater makes this water less dense, and it means that the sinking of that water in panel A can go to the situation in panel B, which is what we call an off state. That's when the overturning circulation is off. It means that basically there's no overturning of water to any large extent. And then if you look in the lower panel D there, you see the heat transport. When you switch the overturning off, we should have made that red curve more like a blue curve there in panel D, because the whole of Europe just gets a much colder climate when it switches off, because that heat transport I spoke about basically collapses from 1 petawatt down to only a fraction, like about 0.2 or so. The total heat transport reaching Europe is decimated, reduced by 60, 70%. And that overturning then changes climate. And I think it's safe to say that pretty much of those, 1,000 or so studies through paleo literature, through modern day monitoring of the ocean circulation, through to projections, it's safe to say that most of them focus on the regional North Atlantic for the climate impact. So that's to say the region around the North Atlantic, the Americas, Europe, in terms of the impacts. Not many of them go and look at the global scale impacts, which is the focus of this study. I guess I want to say 2 quick things before I get on to what we did. And one is that I already mentioned the projections are that this circulation will slow down. There is no single model I'm aware of that does anything but either, most of them slow down a significant amount over the 21st century. So most of them project a significant slowdown. Some project only a very weak slowdown. None of them at all project an acceleration. None of them project that this circulation will pick up. At best, it's relatively stable. But I would say that none of those projections include the effect of Greenland meltwater. And what I mean by that is the coupled ocean atmosphere ice systems we use at the moment, they don't include the effects of melting Greenland ice caps. And the only reason they don't is that we haven't yet developed these coupled global configurations to include the ice sheets of Antarctica and Greenland. I think when these models were first built, we sort of thought, well, these are big stable slabs of ice. We're not going to see them melt that quickly. Let's just not worry about them. And unfortunately, with our emissions of greenhouse gases, 50 years on, so the first models were developed 50 years ago. 50 years on, these modeling systems don't include the ice sheets, and yet we're seeing meltwater dumped into off Greenland and Antarctica at an absolutely unprecedented scale in terms of the rapid melting. 20 trillion tons of water came off Antarctica. Came off Greenland. Sorry, I mix the two continents up sometimes. 20 trillion tons in the last 20 years is a staggering amount. So this is a massive amount of meltwater. By the way, it could be my numbers are across my desk every day in large quantity. It could be 5 trillion tons in 20 years. Anyway, it's a lot. If you actually attribute it to per person on the planet, we can each sort of say we're responsible for thousands of tons of meltwater. And then if we're realistic about attributing the melting to our own greenhouse gas emissions, anybody in North America or Australia tuning in, it's probably 5 or 6 times that amount, because we're emitting more greenhouse gases per capita than many of the other nations in the world. So that's my intro spiel. Are there any questions, Katerina, that's come across your chat there that I should think about?
No, so far everything is no questions so far. Thank you.
Great. Okay, no worries. So well, I guess the best next thing I can do is to skip down to figure 2, which I hope is a really nice overview of where the climate system gets to across about 5 or 6 parameters altogether. Top left, you've got what surface temperature is reached. Top right is where the rainfall patterns change, whether they get wetter or drier. So green means a wetting of the surface of the Earth, and brown means a drying. The next panel down includes 2 variables, both sea level pressure, color contoured on the bottom left, and then the wind vectors, which are unfortunately a little bit hard to see because we had to stipple those little black dots. Means it's a significant change. Unfortunately, those little black dots are so omnipresent on each of the panels. We should have probably stippled where it's not significant, because it was very, very few regions. So it's probably a poor choice of graphics there that we made. So unfortunately, those vectors aren't as clear as I'd like them to be in the lower left. And then on the right is what we call the velocity potential in the upper atmosphere. Think of that as a net convergence of air in the upper atmosphere where it's red, and it's a net divergence where it's blue. And so these diagrams show, if you start with the top left, panel 8, the surface temperature, that big cooling over the North Atlantic, that's the classic sort of day after tomorrow Hollywood blockbuster scenario, big freeze over the far North Atlantic, much colder temperatures. And of course, in a global warming world, greenhouse gases would tend to overwhelm that. And so I should point out these simulations we did, just like a present day model, greenhouse gas concentrations are fixed. And all we do is dump meltwater off Greenland to switch off the overturning. And we look at the difference between this off state minus non-state. And so in this case, this off state has a really cold European North Atlantic ocean temperature, a really much colder air temperature than right across the whole of the Northern Hemisphere, because it sort of basically, spreads via the atmospheric circulation to adjacent oceans and adjacent longitudes. So a lot of it spreads from east to west with the mid-latitude jet there. In the southern hemisphere, it's a completely different story. And I'll start off with the Atlantic. You can see these big red patches of much warmer water, so 2-3 degrees Celsius warmer in some of these patches. Right on the tropics, it's only about 0.5 to 1 degree Celsius warmer, so a couple of degrees Fahrenheit or so warmer right on the tropics there. So right near the equator between Africa and South America, only a degree C or so warmer, but I'll show in a minute. That's very important for changing the atmosphere. And if you can already see that in the precipitation and sea level pressure, all other 3 panels reflect that. And so the green patch in the precipitation there over the South Atlantic, as well as the blues in the lower 2 panels, that shows that over that warmer water, there's an incredible shift in the atmospheric circulation. There's suddenly convective cloud formation, and so you see much more rainfall, but also you see this upward movement of air, and so the sea level pressure gets lower in the lower left, and the divergence of air in the upper atmosphere, so that lower right panel, those blues, the value 7 showing that big divergence of air there, that pushes that's the effect of air rising into the atmosphere from this convective rain cloud formation. It rises deep into the atmosphere, and then that air spreads away from the convection site. And I'm going to get back to figure 6, shows you a schematic of that all put together. And when this happens, we've known for a while now. About 5 or 6 years ago, one of my postdocs, Shane McGregor, did a really nice study that we published in Nature Climate Change as well, that showed that this warmth that you have in the tropics in the South Atlantic, that's a way to change the Pacific. And so that really red patch in the panel D there, that big red patch in panel D, that shows that the air that's rising over the South Atlantic, it actually then converges over sort of Latin America, and it sinks and returns to the surface of Earth there. So there's a lot of downward movement, and that actually drives this trade wind acceleration that you can see on the lower left panel in panel C. Those trade winds accelerating, those big vectors right across the Pacific that blow winds from the Americas across towards Australia and Asia. That's a big acceleration of the trade winds. And that's a really important thing to change our climate. It means that the world goes into what we call a more La Nina-like state. And the La Nina, the reason why we call it a La Nina-like state is that those trade winds that I'm speaking about in panel C there, they're there. So these winds are part of our climate system on average, but in this case, they're accelerated by a massive 30%. So the winds there are 30% stronger. And then the wind stress then acts on the ocean. It pushes a lot of warm water towards Australia and towards that whole Asian, Indonesian archipelago. Gets a lot warmer relative to the East Pacific, and that sort of sets up what we call La Nina-like conditions. And that's why over Australia and Indonesia, in the top right there, that those greens in the precipitation plot, you can see Australia gets much wetter. Doesn't look like much when you first see it, but a millimeter per day is equivalent to 365 millimeters a year, right? So parts of the Australian desert that are quite dry, virtually no rainfall in any given year, really low rates of precipitation. That's a huge boost to inland Australian rainfall. And a huge boost of rainfall right across the Indonesian archipelago. In contrast, you can see over in the East Pacific, especially over Latin America, Peru, Mexico, these regions see a big drop off of rainfall, those browns there, and over all of North America and Europe, also a drying trend there. So, so just to backtrack then, so there's the summary of how the world looks with this AMOC shutdown. It's a global teleconnection, so it's not like this day after tomorrow scenario where only the European and North American continents are affected. You can see an impact all the way down to Antarctica, and I'll talk more about that Antarctic impact a little bit later on. But basically, this paper we submitted it with this narrative of saying, when the AMOC, if and when the AMOC does shut down, we're not just going to see something happening in the North Atlantic, this sort of cool blob that a lot of people are speaking about. Stefan Rahmstorff and others are talking about this cool blob in the Atlantic as already a sort of indicator of the Atlantic slowdown. The global ramifications will reach as far as Antarctica, and that's what this whole paper is about. Is how there are these interbasin and interhemispheric impacts of this global of this overturning the North Atlantic. There are global ramifications reaching into all three basins, Pacific, Indian, and Atlantic, and then reaching as far south as the Antarctic continent. I reckon, Katarina, I should say, I reckon that I could probably skip now and just give a bit of an overview from some of the other diagrams show the sort of decade by decade response. So what we call the transient response. So how the response I've just described, like how does it actually go from when we first apply the anomaly of meltwater, how does it get to that state I just described? So people can read about the time-dependent response, but perhaps the place to finish up before I open for Q&A, which is maybe going to be more fun for listeners to just ask me any question they like about this, is that if you go down to figure 6, it was our attempt to sort of put together a schematic overview of those mechanisms I just described. It's busy in the Atlantic because a lot happens there, but basically when you shut the overturning down, you see a residual of heat building up over the South Atlantic, and that big green arrow that points upward is that convective cloud formation anomaly that I mentioned, and the sinking of air you can see then occurs just over the East Pacific. That accelerates the trade winds. You can see that label there, the intensified trade winds then. So this diagram, at least there's no stippling anymore. You can see the arrows really clearly with the intensified trade winds. That piles a lot of warm water up in the West Pacific, and you get a Rossby wave train in the atmosphere. That's a way that the atmosphere takes that warming signal right down to Antarctica. And the reason why we were both excited and concerned by our results. The reason we're excited is, we're scientists trying to understand the climate system. We feel like this was a piece that advanced our understanding of the system in these ways I've just described. But we were concerned because each of the things I've described there, this intensified trade wind system, the Atlantic overturning slowdown, this buildup of heat in the South Atlantic, and even the Amazon Sea low, that low pressure system off Antarctica deepening and becoming more intense, each of those things has played out more or less in magnitudes that match our simulations. Given we've only had a 20 or 30% slowdown maximum of the overturning, we have seen this intensified trade wind field, the Amazon Sea low deepening, a buildup of heat in the South Atlantic. So each of these bits of the diagram I'm showing has played out in a sort of modest sense over the last 50 years. And so it's almost like if we keep going with an AMOC continuing to slow down, our proposal here is that, on top of the greenhouse gas induced warming of the planet, some of these other changes will be lurking there in the background, driven by this AMOC slowdown. So, Katerina, that's a bit of a 15-minute spiel. It's a new experience for me to give a talk like this without seeing the audience, without showing you slides and being able to point to the features as I described them. But I hope that gave you an overview of the science we undertook.
Yeah, thank you very much. Yeah, it was great having those figures described the way you did. Thank you so much, and please raise your hands if you have questions. I know Eli was looking forward to your talk very much, so Eli, feel free to ask your question.
Sure. Thank you, Katerina. So I was wondering. You mentioned the effect on cloud formation. Is there any sense at all, and I would certainly understand if there isn't, on any effects or changes on cloud albedo and how that could affect the forcing, the radiative forcing that really isn't part of this model?
Yeah, no, it's a good question, because there is whilst there's no radiative forcing from greenhouse gases, like the greenhouse gases we have are fixed. All the cloud cover changes that we simulate, that in this model, they do then affect the albedo, and so over, say, the South Atlantic, where I mentioned there's this big buildup of heat, there's definitely more cloud cover there, and that cloud cover would reduce the incoming solar radiation hitting the ocean surface. But the slowdown of the AMOC is such a big impact that the oceans, that warmth that accumulates there persists, and so even though there's greater cloud cover, that definitely shields the incoming solar radiation. That's a cooling effect over the surface of the ocean, but with the AMOC slowdown, the warmth that accumulates there just off Brazil and off Africa, that's not something that the cloud cover can then, turn into a cooling. That cloud cover effect would reduce the amount of warmth there, but not enough to overwhelm the AMOC effect. And so, the AMOC is such a big ocean heat driver. It sets the whole transport of heat from the South Atlantic into the north. And so, having it slow down, as we've already seen in the last 50 years, it's slowed down for sure from measurements. I think it's pretty hard to deny from paleo records and from measurements that it's had. It has year-to-year variations, it has decade-to-decade variability, but there's very strong evidence in my mind that the AMOC is on a slowing trend over the last 50 years. That's left more heat in the South Atlantic. We've seen that in ocean temperature measurements. That's increased the cloudiness there, and it has probably changed the atmospheric circulation in the same way that we show in this diagram 6 here with these accelerated trade winds. The tough thing is, of course, that in the Pacific, for example, we still have El Nino, La Nina cycles sloshing back and forth. And so when I say a La Nina-like world, it's not like we suddenly get, just La Ninas. It's more, and we're coming up for a triple this year potentially. And so, but that's not to say, these triple events have occurred 100 years ago. An El Nino might be on the cards in a couple of years. So this La Nina-like shift is more, if you like, it's more shifting the probabilistic framework away from an even number of El Nino La Ninas to, a more La Nina-like base climate, and maybe more La Ninas and fewer El Ninos. So, yeah, it's a long answer to your question, but I hope that helps.
So just to refine a little bit and verify a point. Radiant forcing due to cloud albedo and presumably I would guess ice is part of the model.
Yeah, that's right. Yeah, that's
Okay.
right. So the model includes it. So the ice comment I made about there being no Greenland and Antarctic land ice. So these are the big slabs of ice that are basically really stable. They've been stable for the last 6,000 years. We're changing them now alarmingly rapidly. But these are this big stable slabs of ice that the glaciers that build up over land. And so when they melt, unfortunately, they do raise sea levels, but they're built up over thousands and thousands of years by sort of compressed snowfall. That ice is not included in all the global coupled models that we analyze in the IPCC. Those sort of so-called CMIP models that you might see in the literature, they don't include the ice sheets of Greenland and Antarctica. They do include some runoff effects, and modeling groups are presently configuring them, like getting them ready to include those effects. But they do include the sea ice, which is the floating bit of ice that freezes each winter and then melts over summer. That seasonal sea ice over the Arctic and around the Southern Ocean off Antarctica, that's included in these models. But we don't yet have predictions of the full coupled system with this land ice. And I should reassure the listeners that we do model the ice sheets of Antarctica and Greenland. So there are fully configured dynamic models of those ice sheets. And what we do is we force those ice sheet models with the predictions of these coupled models I'm talking about that don't have the ice sheets there. So in a way, we have the two systems operating separately, the full ocean atmosphere sea ice system and actually terrestrial vegetation as well in those full coupled models that we know and love. And then these ice sheet only models are then forced by ocean conditions and atmospheric conditions to predict how the ice sheets will evolve over the coming century. So it's just that the two modeling platforms haven't been jigsawed together into the one modeling platform. And that's a big engineering job. It's a big software engineering job. But here in Australia, in the US, around Europe, Japan, China, a lot of these nations are putting together, they're starting to put together the models. So the ice sheets are fully embedded in those couple models. So they'll respond to greenhouse gases, they'll change the ocean circulation. That might feed back and change the way the ice sheets are being built each winter and so on.
And so is cloud albedo assumed to be a constant, or does it vary to embrace the potential for lower albedo clouds under different conditions?
Yeah, no, it's a fully dynamic, it's fully functional on the clouds you have there. So this model's from the NCAR, the National Centre for Atmospheric Research in Boulder. We run it here in Australia, and actually, even though it's a model built out of the NCAR group there in the US, it's run globally by different climate groups. That model includes a whole number of cloud types, and it's low level clouds, middle atmosphere clouds, and upper atmosphere clouds. So it's got a whole, and those cloud sub models are really an advanced bit of these systems, but it's a bit that you can imagine is tricky, because if you fly up through a cloud system, you can see clouds come in all shapes and sizes and types. But yeah, in this model, it's a fully predictive part of the system. When clouds increase in their coverage, the albedo from those clouds, so highly reflective clouds, will act on that solar radiation and send the radiation back to space in a greater quantity if it's a big fluffy white cumulus cloud compared to cirrus clouds. All those different cloud types are in there, and this model would have had those clouds adjusting. We don't go into the cloud response too much in this study, but there's definitely all the cloud variables are in there, and we could go and piece apart exactly how the cloud cover changed and how it changed the albedo. It's part of the predictive system, but it is when we think about models and where we need to improve their physics, the atmospheric science community will say, oh, we need to get convection in the atmosphere better resolved. It's a very hard bit of the model to because it's highly nonlinear physics. Cloud formation is a very microscale process, and we have these big global models that build the physics in there as best we can. I should point out one thing that we liked about the NCAR model, and we have this in the extended data figures below. There's a whole lot of figures. If people scroll down to, or swipe left or right, depending how you move through the document that you've got in front of you. If you go down that first figure in the extended data, so extended data figure 1 it is, the topmost panel shows panel A. There's a bunch of reds and red bars going downward from a 0 line, and a bunch of blue bars off to the far right. All these acronyms along the bottom are all the different CMIT models. So I won't go through all the acronyms and what they stand for. Some of them are models out of France, the UK, Canada, the US. You can see the model we use is CCSM4. That's the yellow bar there, and this shows the way the Atlantic is linked to the Pacific on decadal timescales. Is actually a measure of the temperature gradient from Atlantic to Pacific versus the trade winds. But it's a really good way, when you try put this panel together for us for the paper, it's a really good way to measure, how much the Atlantic is influencing the Pacific in these models, and the observations there are in green. And so that's the kind. It's not at. It looks like it's at the value -1, but it's close to that value. It's probably -9, -0.9 something. That green bar shows how that Atlantic Pacific influence has played out over the last century. It's a measure of that coupling, and you can see the models go. They're all coupling in the right sign, right? So none of them are positive values. They're all coupling with the right tendency. But some of the models, like the Access 1.0 model at the far right there, that's an Australian model, that really underplays that link from the Atlantic to the Pacific. Now, that Access model may be really good for a different part of the climate. I know it's a really good model, for example, for near Antarctic processes, and the Southern Ocean is really well represented in the atmosphere there. The jet stream there in the Southern Hemisphere is great, but it happens to be pretty bad at that link from the Atlantic to the Pacific. And what we were kind of relieved about, because we started this study before doing a detailed evaluation of the model skill. We just, started this, the PhD student who led the project, Brian Pinto, he started with this model looking at a few different bits and pieces. And once we got interested in the Atlantic influence on the Pacific, that's when we did this sort of check via Wenju Chai's work to see that the model we use happens to have about the best representation, along with the other models there, the Norwegian model, NorESM, and the CMCC model. Both are really good as well. I mean, most of those models in that red zone are pretty good at that teleconnection, perhaps too strong in the CNRM model at the start there. But this is a sort of evaluation that any climate scientist will do. If you're looking at a given process in your model, you do want to go and see whether the bit of the physics you're looking at, the bit of the climate system you're looking at, is it well resolved in that model? And if you see it's got some biases, you pretty much need to abandon the study that you're looking at, because you don't want to use a model that's got underlying biases to look at a bit of physics. You want the model to be reliable in that regard.
Thank you so much for that answer. I have a question in the chat, in the room chat, from Carrie, and she's asking if any of the model effects have are like how they are modeling hurricane formation in the Atlantic, strength and speed, if this will change.
Yeah, it's a good question. Are you still there? Just you cut out the very
Oh
end.
yeah. Sorry, I pressed.
Yeah, good. No, that's all right. I just wanted to make sure I was still online. Yeah, great question. We don't go look at the hurricanes. If you go back up to figure 2A, say, because that's got the sea surface temperature anomalies, we don't look at hurricanes in this simulation, but there would be, tropical cyclones in the atmospheric model. They'd be formed. They wouldn't necessarily be, we don't have the fine scale to resolve them in all their glory, but there's definitely tropical cyclones in the atmospheric model. And with the colder conditions over the North Atlantic and the warmer conditions over the South Atlantic, whether or not there are more or less hurricanes, I wouldn't be able to say, but definitely the cooling effect over the sort of Gulf of Mexico, that would sort of weaken the intensity of tropical cyclones there. Any cyclones in the South Atlantic, they're rare in the South Atlantic because the waters there are normally not quite as warm and conducive to cyclones. But South Atlantic hurricanes would be stronger. The hurricanes we get off Australia, so tropical cyclones in the Coral Sea there with those warmer conditions, would be more intense. And that's, I should say, during La Nina years, one of the risks to Australia is much higher rains, and we've had some terrible flooding events the last couple of years from hurricanes intense tropical storms. They weren't full-blown cyclones necessarily, but we had some terrible flooding events in Brisbane in 2010-11 and in Lismore this year, and parts of the eastern seaboard were dramatically flooded in this double La Nina we've had so far, and that's why a lot of Australians are worried about a triple La Nina coming up. But that warmer condition you can see in panel 2A there, those warmer ocean conditions, that's the sort of thing that would intensify the rain systems in those tropical cyclones when they come along. And we do tend to see, if we look back through La Nina events for Australia, generally speaking, La Ninas see stronger cyclone conditions, or at least when the cyclones come along, they tend to be higher category cyclones because of that warmer ocean water. So the short answer is yes, the tropical cyclones and hurricanes would be impacted by these changes. They'd be impacted big time. We didn't go and study cyclone numbers or cyclone intensity, but certainly, the data's there, and anybody could go and have a look at that if they wanted to in these simulations.
Yeah, thank you so much. Another question we had here in the room, and that I think it's also really interesting, is the oxygen level in cold water is higher, right? As far as I remember.
That's right. Yeah,
um,
yeah. It dissolves more.
so I have issues with opposites. Um, how would the warm water on the southern hemisphere affect oxygen levels, and then the whole ecological system? Is there any predictions into that for
Yeah, no,
for you?
yeah, absolutely. It's a really good question, and I think paleo people go back and look at these eras when the AMOC was off. So last glacial maximum would have been off, and that colder water in the North Atlantic would have meant more oxygen absorption, because oxygen dissolves more in cold water than warm water. And this simulation, this temperature pattern, we didn't carry oxygen as a tracer, by the way. We include temperature, salinity in the oceans, all the ocean circulation, all the physical properties. Same in the atmosphere, humidity, moisture, cloud cover, winds, air temperature, and all these things, pressure. All these things are predicted variables. The pressure is actually part of the model grid, but we don't look at ocean ecology at all in this study. But it's easy to make some summary statements about ocean ecology, and one is that, for example, those warmer temperatures in the Pacific, in the southern hemisphere, would lead to less oxygen uptake. The cold water's more oxygen, but the bigger impact is around these overturning cells. They do a massive amount to regenerate nutrients at the surface, and so unlike the terrestrial system, when we have things die on Earth, they, a tree falls over in the forest, it decomposes, and those nutrients are really important for fertilizing the soil and seeing new growth. It's like a life cycle that we've come to love on the land, but in the ocean, it's a terribly different setup. When things die in the ocean, they sink to the bottom of the ocean, so they decompose and sink. And so the very bottom of our oceans, the seafloor of the ocean, has all of the marine matter that dies out, rains out, and this massive flux of nutrients to the bottom of the ocean. And so these overturning cells, you can imagine, then bring that nutrient-rich water back to the surface. Now, we're lucky that the winds themselves do a lot of overturning as well. So when things die, that a big marine mammal that dies would sink to the bottom of the ocean when it dies, and that's not going to be something that the winds can stop. But a lot of the smaller algae and zooplankton and things that sort of, as it goes through its life cycle, the surface winds over the ocean do stir up the mixed layer, and they keep the mixed layer rich enough in nutrients on their own. But there is a component that's brought back to the surface by these overturning cells, and we have a similar overturning off Antarctica. And unfortunately, under global warming, as we slow these circulations down, because we expect the Atlantic circulation to slow down, we expect the Antarctic equivalent deep and bottom water circulation to slow down. As these cells slow down in the ocean, you can imagine, almost going into a bathtub. If you run your hands to the bottom of the bathtub and bring the water back to the surface, that's the kind of thing that these circulations do to the ocean on a global scale. They bring the water from the bottom up to the surface, much as your hands do in a bathtub, bring that bottom water at the bottom of the bathtub back to the surface. And if you take away that circulation, you're taking away one of the key mechanisms for bringing nutrient-rich bottom water back to the surface. And so there's a real concern amongst the ecology community that over the next century, if we do take away these overturning cells, if we cap them off, if we collapse them over the next decades, even if we slow them down, we're going to be slowing down the regeneration or the return to the surface of these nutrient-rich waters, and that's going to be have a big impact on ecosystems.
So,
Yeah,
you mentioned, that this is an ongoing process, and we've already seen some slowing. I'm wondering if you have any sense whether that can be related to the already observed declines in ocean net primary production.
Yeah, tricky one. I don't, my expertise, I don't tend to cover that literature so much. So I think, I mean, to me, it would be, I mean, you'd see it, for example, in deep ocean oxygen. I mean, these overturning circulation cells very clearly bring oxygen-rich water into the deep ocean. I know there's been studies tracking oxygen changes. The oceans are generally deoxygenating in key places, and that's been used by the physics community to understand potential circulation changes. But the changes in net primary productivity elsewhere, I wouldn't like to comment on, because they could also be driven by wind changes. So there's some big wind shifts that have occurred over the Southern Ocean. Our jet stream is shifting poleward, and that's changing the cycling of nutrients down there as well. So I shouldn't comment on something I don't know that much about, but definitely that any changes in net primary productivity, they're going to have two main sources. One is ocean circulation changes, and the other is ocean biology changes themselves. And so, the ocean acidification community, for example, are very concerned about acidifying oceans impacting calcifying organisms, very small organisms that are at the base of the food, not the very base, that's marine algae, but these calcifying organisms are very important for marine ecosystems. And there are changes afoot for sure, but I don't work in that area of teasing out the circulation impacts versus the biology impacts.
another most important question where your journey started. What will it do to the waves, and what will happen to surfing?
Yeah, no, it's a good question. There's actually a nice report that came out by the Climate Council. People can Google that. It's an Australian group called the Climate Council, and based in Australia, and it's all just funded by the community. It's a community-based organisation. They had all their money taken from the government when we lost a sort of progressive government to the coalition, sort of more conservative government about a decade ago. So it's now all community funded. They had a great report, not just about surfing, but it was about all sports and how they'd be impacted by climate change. And Australia is a very sporting focused nation. We love our water sports and all sorts of sports. And so this was a nice report because it sort of put together a detailed overview of how all of sport is impacted by the sorts of changes we're going to get over Australia. And the reason I point to it is they did include a section devoted to surfing, because it's also a big part of the Australian community is beach going and surfing. And there are all sorts of changes are going to occur, but the main some of the changes actually improve surf conditions, because tropical cyclones are one of the sources of some of the best swells that we get. When a tropical cyclone comes along, it generates swell systems that travel thousands of kilometers, and the further they travel, the better the surf conditions are from those storms. So, we don't have many benefits from climate change, but one of them will likely be more of those tropical cyclone-induced storm systems. Of course, the downside is we don't want these tropical cyclones to be more intense, and so the report was very good and made the point that whilst you might get some better surfing conditions, the very things that create those surfing conditions, the storms, they're also the things that can really damage the communities that support surf tourism. And so who wants to have a world where we get a better surf, but we can't even secure the shoreline through sea level rise and through coastal inundation from big swells and big storm systems? It's kind of like a pretty perverse way to look at it if you kind of say, well, that's great, we've got a better surf on our hands, because the downside will be loss of coastal communities, loss of the option to go and visit a surf break somewhere as a tourist may be gone if that community is being hit by such intense cyclones, and more relevant probably long term, because cyclones you can maybe rebuild some things. But if a storm, if the sea level's rising in an ongoing way, it's taking out coastal communities. That's no good for anybody. So, yeah, that's
Yeah,
maybe
yeah,
best way
I
to summarize
agree.
it.
I'm from Portugal, and Lisbon coastal area has been eaten away recently quite harshly, but has Portugal, I think, has one of the, best surfing areas. But I'm afraid the waves will just get too big. They already have one of the biggest waves in the world.
Yeah, they
It
do,
will
Nazare.
be
Yeah,
way too brutal for
yeah.
everyone. Yeah, but yeah, we have time for a couple more questions. John, you joined, and I saw Jamie unflash your mic.
Hi, Dr. England. In your modeling, the slowdown of the AMOC actually affected the heat distribution within the global. And I'm wondering, do you study the slowdown of this AMOC phenomena would change the global, energy balance, in terms of energy reflection or absorption, the sunlight for the with the Earth as a whole?
Yeah, it's a great question. Thanks for asking that. And the answer is yes. It totally reorganizes the global energy balance. It sees a lot less heat moving in the ocean in the North Atlantic. And of course, part of the global energy balance is set by the sun hitting the top of the atmosphere, right? That sort of sets the overall input of energy onto our lovely planet. And the oceans and the atmosphere both move that heat around within those two systems. And so once you take the ocean heat transport out, the atmosphere then ends up compensating and moving that heat poleward itself. But it's basically it's this ocean conveyor belt in the Atlantic has been so often studied because it does actually set, as you mentioned in your question, it sets the global energy balance at a full scale. It sets how much heat is transported polewards from the tropics to high latitudes, and that therefore with big impacts on climate. I should quickly mention I've got to leave in 2 minutes, so I should go to the next question. So I don't want to leave anybody short if I can.
Thank you very much, Doctor. That's there's so much to think about. But my question was, what system do you actually use to monitor the actual heat of water? Because the ocean's so huge, right? Like, do you just take
Yeah.
small samples and then have a formula? And at what point and depth does it become either not relevant, or is it always relevant no matter how deep and deep and deep you go? That was my
Yeah,
question.
great question. Great question. And there's a whole talk I'd love to give one day just on ocean observations. But I mean, we've had seagoing research vessels dedicated to measuring temperature through the oceans for about 50 or 60 years now. We have surface measurements going back 100 years. We've had satellites sensing the surface of the ocean beautifully, globally high resolution since 1979 for temperature and sea level elevation and things like that. But probably most important to your question for monitoring the overturning circulation, we now have a global array of what are called Argo floats. That's ARGO. These floats are sort of autonomous. We chuck them off a boat. They have an incredible system where the bladder within the system contracts and they become dense. They sink to about 2,000 meters. They sit down there for a period of time, days or weeks. Then they're programmed to then resurface. They then beam that temperature measurement that's from the surface down to 2,000 meters back through a satellite back to people. There's 3,000 or so. There may be more these days. That 3,000 numbers maybe a few years old. It maybe is getting towards 4 now. But we definitely need these Argo measurements because nowadays we can track top to 2,000 meter heat content really well. And before the Argo measurements started in around 2005, we relied on these seagoing transects, which were incredibly costly to run. And the measurements were really coarse grid. You can imagine going to the Pacific and drawing 3 latitude lines, 3 longitude lines. That's what it was like in the 70s or 80s. In the 1990s, you probably have 5 or 6 of those lines crisscrossing the Pacific in both directions, or maybe 8, but still not many. And now with Argo, it's a what we call almost a near global coverage. We don't get under the sea ice. we don't get below 2,000 meters, and that's still something we want to address. But there are some more bottom-reaching Argo floats coming online now. But there's a whole topic, and I've got to get off to another meeting, so I'm going to have to cut out, Katarina. It's been lovely chatting with everybody.
Thank you so much.
Thank,
Yeah,
thank
I
you so much.
appreciate it, and thanks for taking the time.
Thanks,
And
Matthew.
yeah, it was an honor having you, and I hope you have a lot of fun, and it's very important work. Thank you.
Thank you so
Mhm.
much, everybody. I really enjoyed the chat. I really enjoyed joining. I really appreciate your interest in the study.
Thank you.
Thanks very much.
Bye, and enjoy the rest of your day. And yeah, thank you everyone for coming, asking questions, and yeah, being here. Maybe if you have important questions that you didn't get to ask, you can reach out to me, and maybe I can write Matt an email. And yeah, we'll close the room. I'll just make really quick a couple of announcements. Dr. Bennett will be talking tomorrow at noon. He also has an hour, so we'll keep it like today. And he has developed a new treatment target for chronic pain. And then at 9 p.m. EST, we'll have Dr. Congree, 3D printing with light converting nanoparticles. It's a really interesting new technology. And then Dr. Santos, she's a offspring of James Tour's lab, and she will talk about her work that she did at his lab of light-activated antibacterial molecular machines that attack basically antibiotic-resistant bacteria. So yeah, thank you so much, and yeah, I hear you all back soon. Thank you, Matt. Bye, everyone.
Thank you. Bye.
Thanks, Katarina. See you all soon.
Yeah. 3,
Thanks, Katrina.
2,
Bye, everyone.
bye.